Imagine being back in a chemistry lab with your goggles, your lab coat, your maybe some gloves on. You go to do an experiment with acids and bases, and you go to pick up your acids, and one of them is just labeled vinegar with nothing at all additional on it, and the other one's labeled hydrochloric acid with a big danger label on it. So the big question is, if they're both just acids, then what's the big deal? Why am I wearing all this protective equipment for just some vinegar, and why is there the big warning label on the hydrochloric acid? What is it going to do to me? Why is it so much more hurtful? So the root of that question really is, what is the difference between a weak and a strong acid? And over the course of this video, we're going to do a little review to start, but then we're hopefully going to go in depth in determining what is a strong acid, looking at how to determine what that is, and then how to compare the strengths of two weak acids with some numeric values. So hopefully you learned something, and we'll jump right in. Let's start out with some review. First, we're going to tackle the Bronsted-Lowry definitions of acids and bases. According to the Bronsted-Lowry definition, acids are proton donors, or they lose H+, or sometimes referred to as H3O+, in hydronium ions is what they're referred to, in a solution reaction. And bases are proton acceptors, or they gain H+ or hydronium ions in a solution reaction. So let's take a look here. And we'll kind of keep these in mind, and we'll move it up just a little bit. And in this chemical equation, we have H2CO3 plus hydroxide, and we've got it a little reaches equilibrium in solution when and it results in HCO3 minus plus and a water atom here. So in this particular example, the H2CO3 results at the other end of the reaction as HCO3, and it's obviously lost at hydrogen. It's lost that H+, and therefore it's donated its ion to the reaction. So that makes the H2CO3 our acid here, and the resultant is its conjugate base. Now, by the same rules, we've got our hydroxide here, the OH, and that is on the other side of the reaction going to H2O. So this is accepting, it's gaining that H+ ion, that hydronium ion, and so this OH is going to be what used to be a conjugate acid. It therefore accepted, and the H2O as the accepted compound is considered the base according to the Bronsted-Lowry definitions. Now, last thing to review here is a list of 7 strong acids and 8 strong bases. Now, I put the bases in here just as kind of more of an FYI. We're generally going to stick to the acids here today in this lesson, but as you go farther into your book, you will need to know how to do similar things with bases as well. So our 7 strong acids are listed right here, and we should definitely try and memorize them, or at least have this list handy as we go through our next lesson, 17.4 here. Continuing on, 17.4, acids and their strengths and the acid ionization constant Ka. So to start off with, we'll go over some strong acids. So strong acids, according to the Bronsted-Lowry, they completely disassociate in solution. This means that they're going to yield the greatest amount of hydronium ions whenever they're kind of interacting with another aqueous solution. So they're going to donate 100% of their hydronium ions into to the conjugate base. They generally have large Ka values, And here's a little bit of an indicator that a strong acid is present. And strong acids in aqueous solution, they do, just like we said, they completely disassociate. So that's going to only feature one arrow in the chemical equation. So that's a little bit of an indicator that a strong acid is present when determining if an acid is a strong or a weak acid. For weak acids, they do not completely associate in solution. So there's going to be a little bit of a back and forth there. Some of the hydronium ions are going to go from one side of the A side of the reaction to a B side of the reaction. But also there's going to be a little bit of a reversible as well, where a little bit of the hydronium is going to come back towards its conjugate base side, just because there's a little bit more of an attraction. And that leads to the second point. The degree to which the hydronium dissociates depends on the attraction strength between the H plus and the conjugate base. And later on in the chapter, we're going to go through, calculating exactly how much which one's more attracted to another, how we're going to determine that. But for now, we're just going to go ahead and settle with this definition that just the attraction strength determines the dissociation of the hydronium in a weak base. And lastly, there's a dissociation constant, Ka, that actually places a value on how much hydronium dissociates in each weak acid. Now, some of these constants are known, and they're listed in the book on page 739 if you'd like to look them up. But some of them you'll also be able to calculate if you have all of their concentrations present. So let's go ahead and move on to an example. When determining the strength of an acid, so let's look at this equation here real quick. We've got H2CO3 plus your water going to HCO3 minus plus a hydronium ion, right? So first thing you want to do is ask yourself a question. What is it? One of the strong acids that we went over. So we can review our list, have it handy. Hopefully we have it memorized at some point. And we know that H2CO3 is not on that list. So that's a good indicator that it could be, it's probably not a strong acid. Secondly here, we can ask ourselves, are there any other indicators in the chemical equation? Looking specifically at the equilibrium arrows. So we have the equilibrium arrows here. That means that there's a little bit of a back and forth on this equation. It can go forwards and it can go reverse. That's usually indicating a partial dissociation of hydronium. And therefore, you're probably can assume that it's a weak acid present. So now that we've determined that the H2CO3 is a weak acid, we can actually write an ionization constant formula, a Ka formula for that acid in this equation. And again, that's the number we can place on any weak acid to determine its relative strength and kind of compare two weak acids, which one is stronger, which one is not. And like I said, we went over the known values, which are listed in our book. But it can also be calculated if you were given concentrations using this formula here, where Ka is equal to the hydronium ion concentration multiplied by the concentration of the conjugate base and divided by the concentration of the original acid. All right, so hopefully, I know I went over quickly those two examples in the lesson plan. Hopefully you got a chance to pause it and rewind it if you needed to. But right now I want to go into just a problem that you can try here for yourself. And we've got it as follows. We've got to determine the acid in each chemical equation and indicate if it's a strong or a weak acid. And if it's a weak acid, we want to write a Ka equation for it. And I know we're not going to be giving concentrations yet. We just want to write the formula as if we were given concentrations. So if we do find them in an experiment, we could just plug them right in and we don't have to do anything extra. Now I'm going to show you the problem, A, B, C, and D here. All four chemical formulas, all four contain acids. You just have to figure out which one is weak, which one is strong. And you can go ahead and pause the video now. Go ahead and do that, and we'll go over the answers in just a second. Okay, hopefully we got through these pretty well. We'll kind of go over the answers here. So HNO3, first off, is a strong acid. It's one of our strong acid listed on our strong acid list. So that was the first kind of giveaway. Also, your in this equation, the single arrow means the complete dissociation, and the complete dissociation of hydronium ions is an indicator that it's a strong acid here. The CH3COOH, that would be our weak acid, and its Ka is going to be its hydronium concentration multiplied by the concentration of its conjugate base divided by the concentration of its acid to start with. CHBr, it's going to be a strong acid again. We've got a single arrow right here, another indicator, and it was one of those strong acids on our list that we wanted to memorize. So 2 indicators, those should be pretty easy for you to kind of pick out by now. And the last one, H2SO3, it's a weak acid, and this its Ka is going to be its hydronium concentration times the conjugate base, which is HSO3 minus, and divided by the concentration of that acid, H2SO3. So if we were given concentrations, we could plug all those numbers in and get a real value for Ka, or if we knew just a couple and the value for Ka, we can definitely use some algebra in order to solve for one of these concentrations if we were required to. So after going over the differences between the strong and the weak acid, doing those example problems, you're asking yourself, hey, I can determine on paper in a chemical formula what is a weak acid. I can do its Ka formula. I can do this, but it didn't really answer our original question: is why is one so much worse for us than the other ones? And the answer lies within that discussion when we were talking about the hydronium concentration and the complete or incomplete dissociations. Now, if you have a very, very strong acid, they're going to have a lot of dissociated hydronium ions. And if that were to come in contact with your skin, which is largely made up of hydrogen, oxygen, carbon, all atoms that could take on a hydronium. If there's a large concentration of hydronium ions present from a strong acid, what can happen is those hydroniums can attach themselves to structures like your skin, per se, to the protein structures of your skin. And what it does is it adds a little bit, it offsets the charge a little bit of that protein. And if it's offset enough, that protein will actually start to lose some of the forces that's holding it together, and it'll start to collapse. And that's what's happening when your skin is burning. Is it's the proteins of your skin are literally collapsing due to this acidation, and it's through a process called denaturation, and it obviously hurts a lot, and you're going to be left with a scar. So you definitely don't want to spill or pour strong acid on yourself, on your direct skin, or any part of you. And that is why we wear so much protective equipment when handling strong or weak acids. Sometimes we can mix them up, so it's always good to be on the side of precaution. Hope you enjoy the video.